Dear colleagues, let's start our morning session. And our first speaker today is Youl Lee at Busan National University with the talk, A Construction of Invariants for Dichromatic Links by using quandle cocycle pairs. Youl, please.
Yes. Let me start.
Yes.
Okay. Thank you. First of all, I'd like to thanks to the organizer to give this opportunity to give a talk in this great conference. These are the outline of today's talks. First, I'd like to review some basic notions about the dichromatic knots and links and diquandle counting invariant of dichromatic links. And then I'd like to give a construction of state sum invariants for dichromatic links by using quandle to cocycle pairs. And then I want to introduce state sum invariants for dichromatic links via shadow quandle to cocycle pairs. Actually, this is using region colorings of the diagrams. And final section, I want to explain some computations of the state sum invariants and non-trivial examples. Okay, here's a definition of a dichromatic link. Dichromatic link is smooth embedding of n circles in three space that has two labels represented by 1 and 2. When each component of L is oriented, L is called oriented dichromatic links. As usual, unoriented dichromatic link R3 is represented by a diagram, actually oriented diagram in R2, which is a classical oriented link diagram that has the label 1 or 2 for each component. Here's examples of oriented dichromatic link diagrams. So you can see the only difference of the classical link diagram is the these labels for each component. Okay, you can see easily. Two dichromatic links L and L prime in 3 space are equivalent if they are ambient isotopic and preserve the component labels in the 1 and 2. Two dichromatic links L and L prime are equivalent if and only if their diagrams D and D prime are transformed into each other by a finite number of randomized moves preserving the levels of each component. So this is randomized moves for dichromatic link diagrams. Actually, these three are randomized moves with component label. Here's I and J represent component label 1 over 2. All components of a dichromatic link may have the same label, all 1 over all 2, and such a dichromatic link is a monochromatic link. actually monochromatic link can be regarded as a classical link, just deleting the labels. So dichromatic link theory is a generalization of the classical link theory. An interesting dichromatic link is one trivial dichromatic link. So one trivial dichromatic link is a dichromatic link in R3 over S3 having at least two components, and one of which is unknotted and labeled 1, while all other components are labeled 2. One trivial dichromatic link in 3 sphere corresponds in obvious way to a link in a solid torus. Indeed, regarding S3 as the union of the solid torus V and another unknotted solid torus U, you can see these pictures. Any link L in our solid torus V, here's our solid torus V, can be represented by a mixed link L prime. L prime consisting of the C. C is the complement, the core of a complementary solid torus U, and our link L in the solid torus, which is a classical link in 3 sphere. There is a link in some way with the cocycle C of the fixed complementary torus part U. The mixed link L prime gives naturally one trivial dichromatic link in S3. Actually, this picture shows this correspondence. This C is this C comes from the core of the solid torus, and this is our link in solid torus. Okay, so this is a mixed link, and if we change the cocycle C to the unknotted component and give a label 1, and all the other component, actually the solid torus link L, have the label 2, then we can obtain this one trivial dichromatic link from this mixed link, and vice versa. You can easily see the converse. This diagram is the projection of this link into a plane. This is called an analysis diagram, or some people call the punctured diagram of a solid torus link. So solid torus knots and links can be understand the one trivial dichromatic link. Now we move to the some algebraic notions. Quandle is a set X equipped with a binary operation. This I call the triangle. Okay, satisfying the following condition. The first condition is this one, the idempotent row, and the second condition. So for any given two element X and Y, there is a third element Z such that X equals G triangle Y. And for any three element X, Y, Z, this self-distributive laws is satisfied. A quandle X with a binary operation triangle is denoted by the pair usually. We remark here that the condition Q2 can be replaced as follows. There exists another binary operation delta triangle inverse such that for all xy in X, this identity is satisfied. In this case, the new operation triangle inverse is called the dual operation of the original operation triangle. And it is easy to check this is also quandle and called the dual quandle of the original quandle. A typical example of a quandle is this dihedral quandle of order n. Rn is the set of n element 0, 1, 2, n minus 1 with the binary operation defined by this formula. Then this forms a diquandle and called dihedral quandle of order n. Now I want to introduce the co-orientation and the source region of a diagram. They be a classical or a dichromatic link diagram in plane. The co-orientation of an arc D is a normal vector indicated by usually an arrow like this on the arc, satisfying the pair, the orientation of arc, in this case this orientation, and normal vector n, this normal vector, matches the right-handed orientation of the plane R2. In this case, the normal vector n is called the co-orientation of an arc of D. And among four quadrants around crossing V, the unique quadrant from which all co-orientation of the two adjacent arcs are pointed outward is the source region of this crossing. So this is the source region, okay? The co-orientation is pointed all outward, and also this is a source region. In this talk, which will be indicated by this symbol. And in this talk, a classical or a dichromatic link diagram means always oriented diagram and with co-orientation, otherwise stated. Now we can define quandle coloring. D be a classical link diagram, and AD the set of all arcs of D, and X triangle is given quandle. Then a quandle X coloring of D is a map of the set of arcs to the quandle X such that at each crossing we have this coloring conditions. Okay? This is a co-orientation of oval arc. Then the coloring of under arc is acted by Y, gives the coloring of this under arc. In this case, we use this operation X and Y. And similarly, this is the co-orientation of arc. Then the input color is X, and this input color is acted by Y, gives output X triangle Y. Okay? You can see easily. See the color rule from these pictures. By using this kind of quandle X coloring of a classical link diagram D, one can obtain many invariant of classical links in 3 space and also surface links in 4 space. For example, quandle coloring numbers and its various kind of enhancement. For example, homomorphism enhancement, ride enhancement, or something like that. And also quandle 2 and 3 cocycle invariant and shadow quandle 2 and 3 cocycle invariant. So the aim of this talk is to introduce diquandle coloring numbers and the state sum invariant for dichromatic links by using quandle 2 and 3 cocycle pairs, following the method of the case of classical link case. So actually we want to generalize this kind quandle cocycle invariant to dichromatic links. So we need a definition of a diquandle. Diquandle is ordered triple set X and 2 binary operation, triangle 1, triangle 2, satisfying these 3 actions. The first action, X triangle 1, X triangle 2 are both quandles. And action 2 and 3 set some this kind of distributive law. We call the right distributive laws are satisfied. You can see these 2 actions actually gives some interaction of these 2 quandle operations, right? Equivalently, we can define diquandle like this. The diquandle is ordered quintuple set X and 4 binary operations, satisfying the Q1 idempotent laws, and the second action, this identity are satisfied, and DQ3 is right distributive laws. Okay, this one. Anyway, we can use these 2 definitions. There are many examples of biquandles, but I want to give us some simple examples. Let X be a quandle and the star be a trivial operation defined by this form. Then this triple and this triple are all diquandles, so which is a quandle diquandle. Actually, this is a trivial operation, so this algebraic structure is nothing but quandles. In this sense, we call this diquandle, quandle diquandle. Otherwise, it is called non-quandle diquandle. And we can easily check that this is also diquandle. Okay? One of non-trivial example is Alexander diquandle. The lambda is a Lorentz polynomial ring with 2 variables, and X be a lambda module, then define 4 operations like this, then the lambda with these four, some lambda module X with these four binary operation gives diquandles called Alexander diquandle. Usually, we will use the finite quandles to compute some invariants. So I like to introduce a few things. There exists only one quandles and only one diquandles of order 2. And there are exactly 3 quandles and 7 diquandles of order 3. So these are example of order 2, and these are this is an example of order 3. And order 4 case, there are 7 quandles and 27 diquandles of order 4. So this is one example, like a diquandle of order 4. And X and Y are 2 diquandles. A map from X to Y is called homomorphism. If this map resolves diquandle operation like this. If homomorphism is bijective, then it is called isomorphism. Now I'd like to introduce diquandle coloring. DV now is dichromatic link diagram. The AD denote the set of all arcs of D, and the X triangle 1, triangle 2 that is given a diquandle. Then a diquandle X coloring of D is a map from the set of arcs to the given diquandle X, such that at each positive or negative crossing, we have these coloring conditions. It's similar to the classical case, but we should care of these labels for the case of a dichromatic link diagram. So this is the co-orientation of overlap. Then this is input color and this is output color acted by these colors of overlap. Then here we use the operation delta J. Okay? The J is corresponded to the label of overlap. So this is important. Okay? In this case, also this co-orientation is like this. Then this is input and this is output, and this color is action color. So X is acted by Y gives this diquandle element here. Also, this J is corresponded to the label of overlap. The resulting pair of DC is called X-colored dichromatic link diagram by coloring C. And the set of all this kind of diquandle X coloring of D is denoted by this notation. Then we have this lemma, D and D prime be two dichromatic link diagram. They can be transformed into each other by oriented generalized Rademacher move. Then for any finite diquandle X, there is a one-to-one correspondence between these two sets of colorings. So from this lemma, we have this theorem. Let L be an oriented dichromatic link R3 and D be a diagram of L. Then for any finite diquandle X, the cardinality of this set is invariant of L. So this invariant is called diquandle X coloring number. or diquandle counting invariant of L, and we did not get this notation, so we have this one. The proof of lemma is easy. So we consider diquandle colored light must move here. Then remember that the outside of these moves are all identical. So we fix a color, then the moves before and after, the coloring of the outside is all the same. So to prove this lemma, we have to the coloring of the given diagram D gives uniquely the color of the moved this move. But look at this move. This coloring X is X delta IX because orientation is like this, though this orientation here. So, and this is the same arc, so the coloring is X. So the coloring of this under arc X delta IX, but this is X by the action of the diquandle. And same reason, this is X. Okay, so this coloring determined uniquely this coloring, and also this coloring determined uniquely this color. And similarly, these all moves determined given coloring of D gives the unique coloring of D prime and vice versa. In this move, X, Y, Z actually determined all coloring of the arcs. But this X, Y, Z, this X, Y, Z is equal, and the G, Y delta K, Y delta K. But this 2 is equal by diquandle action. Okay. So this picture shows the coloring is unchanged by the colored light must move. Here's some examples. XY, the 5-element diquandle with this operation table. Then we examine the coloring numbers for these 8 dichromatic links in the first page. Okay. Yeah. This 8 diagram. The computation result this table. So look at this table, then the quandle counting number distinguish all these 8 dichromatic links, so we can see. As in the classical case, we can also define the fundamental diquandle of dichromatic links. L is dichromatic link and D is a diagram, and alpha n and alpha m are all arcs in D. Then for each arc alpha I, take a diquandle generator xi. And for each crossing V, xyz is the arcs around the crossing V. Then we assign the diquandle relate RV like this. Actually, this is identical to the diquandle coloring conditions. Then fundamental diquandle of L is a diquandle with a diquandle presentation like this. Then this fundamental diquandle is invariant of L, of course up to diquandle isomorphism. And the diquandle coloring number is equal to the number of homomorphism from this diquandle, fundamental diquandle to the given quandle X. It is a similar result to the case of classical links. And also we can consider various enhancement of this diquandle counting invariant. And they gives an invariant of diquandle dichromatic link. Now we move to the status sum or construction of status sum invariant for dichromatic links. Let me first recall the definition of a quandle to cocycle. X delta be a finite quandle, A be an abelian group, then an homomorphism from, actually this is reg to chain group, and A is abelian group. I'm sorry, I can't define exactly what this is, but anyway, I think you can familiar with the quandle homology, then you can understand what is this. Anyway, this is maybe the two cocycle of the cochain complex, if and only if this map satisfies the following two conditions. Phi xx equal 1, and for any to the element x, y, z, this identity is satisfied. These two conditions are called quandle to cocycle condition of quandle X. Then a map x product x to A over homomorphism satisfying this quandle to cocycle condition is called quandle to cocycle of X. Now, for given this quandle to cocycle, we want to construct some invariant for dichromatic links. This is given data. Dichromatic link diagram D with co-orientation and the diquandle X coloring C, and the finite quandle X and abelian group A. In this case, whose operation is written multiplicatively for our convenience, and a pair of two maps or homomorphism, then we can define for each vertex the Boltzmann weight like this. Again, this is a co-orientation of over arc. Then this coloring satisfies the color of under arc is acted by Y gives this color of this under arc. Okay. discoloring satisfies this coloring condition, and this is a source region, then we define Boltzmann weight at this vertex B. This is a source region, and the X and the Y is the color of the adjacent edge of this source region. Then we compute pi j xy. We evaluate pi j given map pi 1 or pi 2 at these two color. Okay? Similarly, negative crossing we evaluate, and here's the crossing sign. Then the product of all these vertex weight is denoted by this notation, B phi dc. Then we have this lemma. X delta 1 delta 2 will be a finite diquandle, and phi I is diquandle X triangle I. Product this diquandle A be a map or homomorphism. So this I is 1 over 2 to correspond to exactly the quandle triangle 1, quandle triangle 2. Suppose phi I satisfies this condition. Pi I xx equal 1, and for each I 1 and 2, and any 3 element x, y, z, this identity is satisfied, then this product is unchanged under the diquandle x colored Rademacher moves. So that this means for given color C, that this is the invariant of the colored Rademacher move. Proof is also very easy by considering the Rademacher colored Rademacher moves. Consider this move. This is a source region. So the coloring of the adjacent edge is all the same, X. And also, this is a source region, and the color of the adjacent X is all X, but this is positive crossing and this is negative crossing, so -1 is here. But the condition 1, this condition, this is all 1. So the same. This is a present contribution of this product. Okay. And similarly, we can compute weight these two vertices. This is a source region, so the vertex weight is this one. And in this case, this is a source region, so the vertex weight is this one, but these are inverse each other, so this is 1. So there is no contribution of the product of Boltzmann weight. And calculating the Boltzmann weight of these three coloring gives these two values. But this condition gives this is equal. Okay, so these three moves also doesn't affect product of the Boltzmann weight. So actually this condition come from this quandle colored Rademacher moves. Okay. X will be a finite quandle, and phi 1 is a 2 cocycle of this quandle, and phi 2 is quandle 2 cocycle of this quandle. Then the pair of these two quandle cocycle is called the group pair for this diquandle if phi 1, phi 2 satisfies these conditions. Okay? This condition is just this condition. Then we have this theorem. X delta 1 delta 2 be a finite diquandle and D be a dichromatic link diagram. Then for any given group pair of quandle 2 cocycles for this diquandle, then the state sum defined by this formula is a invariant of a dichromatic link represented by V. So this is a product of a vertex weight for given coloring C. So summing this product of all coloring, diquandle coloring, then gives invariant for dichromatic link represented by it. Now I want to generalize this construction by using the shadow quandle 2 cocycle pairs. To do this, we need the notion of a diquandle X set. X triangle is the quandle, and as you know, the associated group of this quandle is a group defined by group presentation. This group presentation. Then quandle K is an X set of quandle X is a non-empty set Y with the right action of this associated group. Similarly, we can define diquandle X set like this. X triangle 1, triangle 2 be a diquandle, and GXI be the associated group, this quandle. Okay? Then diquandle X set is a non-empty set Y with two right action of these two associated group. We also use this action, the symbol delta 1, delta 2, the same, just the same as the operation symbol. This is usual in the quandle theory, such that for any element U in Y and diquandle element XY, and for any ij, this identity is satisfied. Then this set Y with the two right action is called diquandle X set. Actually, you know, this is the diquandle, and Y is X itself. Then we can define for each I the right action of this associated group on Y, the diquandle operation. Okay. Sorry, this is quandle operation delta I. Then automatically this condition is satisfied. Actually, this condition is just self-distributive row in this case. So Y is a diquandle X set. This is a typical example of diquandle X set. Then shadow diquandle coloring is defined as followed. Given a finite diquandle and the diquandle X set Y and the dichromatic link diagram, and we consider the set of complementary regions of D, RD, and the diquandle X coloring C. Then shadow diquandle XY coloring of D is mapped from this set to this set, satisfying this tilde maps AD to X and the region maps to Y. Okay, and the restriction of this C tilde gives a given diquandle X coloring C. This one. And the two adjacent regions F1, F2 are separated by an arc like this with a label I. And the co-orientation of this arc is like this. Then C tilde satisfies this region coloring condition. This one. This symbol denotes the set of all shadow diquandle XY coloring of D. Then, as in the case of diquandle coloring, we have this lemma D and D prime, two diquandle link diagrams transformed into each other by randomized moves. Then these two sets are one-to-one correspondence. So we have this theorem. The number of the cardinal of this set is invariant of dichromatic linking. So this invariant is called shadow diquandle XY coloring number and the shadow diquandle counting invariant. Our proof is similar to the previous case. So I want to omit. Shadow quandle to cocycle is a homomorphism is two cocycle of cochain complex if and only if phi satisfies this condition. These two conditions are called shadow quandle to cocycle condition. It's similar to the case of just the quandle to cocycle case. So I think we may skip this one. Then shadow Boltzmann weight is defined like this. This is source region. Then we evaluate given map shadow diquandle to cocycle the UXY. The U is the color of region, source region, and the X is the color of under arc, and Y is the color of the over arc adjacent to this source region. Okay? And the negative crossing is also similar, but the crossing sign is here. Then diquandle X, given diquandle X and diquandle X set Y, and a map phi I is satisfies this condition, then the product of this shadow Boltzmann weight is unchanged under the shadow diquandle x-colored Reidemeister loop. So similarly, we can define good pair of shadow quandle to cocycle, satisfying this condition. This condition comes from this one. Actually, this comes from the third Reidemeister moves, right? Then this state sum is invariant of dichromatic link represented by it. Okay, time is over. So I want to stop here, but just this state sum invariant is actually there are many good pairs of quandle two cocycles. This example gives us the things. And we compute the state sum for this diquandle coloring. Then we have a non-trivial result like this by using dihedral quandle of order 4. So this state sum distinguishes these all dichromatic rings. Here, these are all labeling is 1, okay? This is all labels are 2, the monochromatic ring. Anyway, this state sum distinguishes these all dichromatic rings. Maybe I stop here. Thank you very much for your attention.
Thank you. Let's thank the speaker. Maybe some comments and questions. Yes, please.
Excuse me, I asked a question in the chat about possible state sums. So actually, recently it's a small comment. Recently we understood that state sums for many invariants like Day-Graph-Witten can be expressed in terms of our new method, photography method, and actually more or less all cocycles can be thought of as volumes of tetrahedra and several other things. So I wonder whether your invariants fit into that general method.
Actually, I don't know. I have no idea.
I have a question. In your construction, you use good pairs in two sense for general colorings and shadow colorings. Is a way to construct a chain complex and corresponding co-chain complex such that these good pairs are elements of cocycle groups? Because you take two elements from the same cochain group and says it's good or not good and so on. But is it possible to construct one chain complex for pairs?
Actually, that is the other very natural questions. Actually, first I want to construct some homology theory, gives us some diquandle cocycle. But I didn't succeed now, so I use actually two quandle cocycle pairs. But actually this example Actually, there is a method to compute quandle cohomology for finite diquandle case by using just some linear combination of the characteristic functions. Okay. Using this method, we can find the good pairs of the quandle to cocycles and also shadow quandle to cocycles. But I don't know some theory of to find such a good pairs of the quandle. Anyway, this example show that for given a fixed dihedral quandle of order 4, there are infinitely many pairs of quandle to cocycles. Sorry.
Thank you very much. Yes, I understand your answer.
Thanks. Any more questions?
Thank you for the talk. I have some question in the chat line. Could you read it in the chat line?
Thanks. So may I stop share?
All right. So what is the motivation of co-orientation and short reason? So what is the nature of these two things?
I'm sorry. Your question is?
Could you read it, the question in the chat line?
Chat line.
Yeah, in the chat, Zoom chat. Yeah.
Zoom chat.
Okay. What is the motivation of the co-orientation and short reason? Why did you need those two things?
Yeah, actually, we to evaluate to define the Boltzmann weight. Okay, we need evaluate some cocycle and some values. Then in that case, we fixed one region by using the co-orientation. So the co-orientation is naturally defined from the oriented, not the diagram. So we use that one.
Okay, so the second question is, could you provide a precise example that of this structure? Because you give a lot of axiom for this structure, and maybe it turns out that the structure is only trivial. Do you have any precise example of that structure?
Precise example means some computation example of the state sum?
Yes, yes.
I think this example is such a example.
Oh, yes. Yeah.
We compute this for dichromatic links. The state sum are this one. Okay. This is the explicit computation of our invariant.
And the Boltzmann weight is something like the potential of the structure, right?
Yes. Yeah, I think. Yeah, Boltzmann weight is many various shapes. So I don't know what you mean, but you may.
Okay, thank you.
Some kind of potential that you can consider.
Thanks. Let's thank the speaker again.